So in this video, we're going to talk about why the solubility rules are particularly useful to us. And one of the biggest, most important things we can do with the solubility rules is to use this solubility behavior, this idea of when is it soluble, what does it precipitate with, to figure out the identity of an unknown solute. So this type of analysis is known as qualitative analysis because it doesn't really involve any measurements. You're just making observations about the chemical properties of your unknown to figure out what it is. So we're actually going to do an experiment and collect some data and analyze that data to do just that, see how we can apply these solubility rules to determine the identity of an unknown. So what we're going to do is perform a series of reactions in order to identify an unknown ionic compound that we're going to call MX, just to have some kind of placeholder names, where M is our cation and X is our anion. And we have a short list of possibilities. Just to keep this relatively simple, there are 3 possible cations that could be in our unknown. There are 3 possible anions that could be in our unknown. So all we're going to do is react this unknown MX, whatever that may be, with a few different other substances and see does it precipitate form in each case. So before we do that, I want to talk a little bit about what we would expect from each of these. So we'll come back to our solubility rules in a moment. So we're going to do 4 different reactions. Our unknown is MX. If we react MX first with sodium sulfate with Na2SO4. We can think about what will happen. When these 2 things react, they will undergo a double replacement reaction where our cations swap partners, just like normal. Now, we can't figure out exact formulas for our products, but we know how the ions are going to be paired. So sodium is going to end up paired with X in some ratio, doesn't really matter, and our cation M is going to end up paired with sulfate. So these are our 2 products. We don't know what X is and we don't know what M is yet, but that's okay. This is going to help us actually. So the first thing we should notice here is that sodium salts are always soluble. If we look to our solubility rules, Na is listed as generally soluble with no exceptions. So we know that this is going to be soluble just from that one solubility rule. There is no way that this product, regardless of what X is, could possibly be our precipitate. However, sulfate is usually soluble, but it has some exceptions, and a couple of those exceptions are on a list of possibilities for what our cation could be. If we look back at that list, our cation could be barium, lead, or potassium. So barium and lead are both exceptions, meaning that if our cation is either barium or lead, it would be not soluble. So if M is barium or lead, then this would be not soluble, meaning we would expect to see it precipitate. However, if our cation is potassium, which was our other option, then this guy would be soluble, so we would expect to not see it precipitate. So just by mixing our unknown with something else and seeing what happens, we can narrow down what the cation could possibly be. Based on the options we were given, if no precipitate forms, it has to be potassium. There is no other choice. If a precipitate does form, we've at least narrowed it down to 2 different options. So we can take the same kind of approach with other reactions. So the next reaction that we're going to do is with sodium iodide. We can do the same type of analysis. If we react MX with sodium iodide, we mix these two things together, they shuffle around their ions, we end up with sodium paired with X and M paired with I. So once again, we have a sodium compound here, so we know that that's going to be soluble. But this may be soluble or might not be soluble, depending upon the identity of our cation. So if we look at the rule for iodide, we see that silver, mercury, and lead are our 3 exceptions. Lead is the one possible cation that is one of our possible cations. So if our cation is lead, then we would expect this to be not soluble, and we should see a precipitate form. But the other 2 are soluble. Both barium and potassium are soluble when paired with iodide. So if either of those is the correct identity of our unknown, then that product would also be soluble, and we would expect to not see a precipitate from that. So our first reaction helped us distinguish potassium from the other 2, and then the second reaction will help us distinguish between lead and barium. So we're kind of narrowing it down systematically to see which cation it is between these 2 reactions. And our other 2 reactions are going to help us sort out the anion. So the other ones we're doing are reactions with silver nitrate and with calcium nitrate. So if we react our unknown with silver nitrate, again, we will switch partners here, and M will end up with nitrate, silver will end up with X, with our anion. So in this case, we know that this nitrate compound is going to be soluble. Again, if we flip back to our solubility rules, nitrate is one that is always soluble with no exceptions. So no matter what the identity of our cation is here, this is going to be soluble because nitrate is always soluble. But our silver compound here is sometimes soluble and sometimes not. So considering our options for X could be nitrate, chloride, or carbonate. If we look at the solubility rules for those, silver is an exception for chloride. Forgot which halide it was for a second. So chloride is usually soluble, but not with silver. So if our anion is chloride, we would expect to see it precipitate. And carbonates are just not typically soluble with much. Silver is not an exception, so we would expect to see it precipitate there as well. However, nitrate, our other option, is soluble with everything, so we would not expect to see it precipitate if our anion was nitrate. So in this case, if X is either chloride or carbonate, then we would expect this compound to be not soluble, which means we would see it precipitate. But if our unknown anion is nitrate, then this would be soluble, so nothing would really happen. We would expect to see no precipitate or no reaction. So this reaction helps us separate nitrate from the other two. So now we just need a way to distinguish between these two things. So that was with calcium nitrate, was our last reaction. So we'll take our unknown and react that with calcium nitrate. So when we mix these two guys together, swap their ions around, we will get something where M is paired with nitrate in some way, and calcium is paired with X in some way with our anion. So once again, nitrates are always soluble. So this product is definitely soluble. We don't need to worry about that one precipitating. But this guy will precipitate with some of our possible anions and not others. So looking back to the solubility rules, again, too far, there we go. We know that nitrate is always soluble with everything, so it won't precipitate with calcium. Chloride is usually soluble. Calcium is not an exception, so calcium paired with chloride would be soluble, and we would expect to not see it precipitate. But carbonate, usually not soluble. Calcium is not an exception, which means that there would be a precipitate there because the product would be insoluble. So if our anion is calcium, then this product would not be soluble in water. So we should see a precipitate. If it's either of the other two, if X is, oops, I did this wrong, sorry. If X is carbonate, my bad. We would expect to see a precipitate because calcium paired with carbonate would not be soluble. If X is chloride or nitrate, then this product is soluble, which means we would see no precipitate. So now that we kind of have everything spelled out for what we could expect here, we can actually go and collect the data. Here I have 4 samples of my unknown in test tubes. So we're going to do those 4 different reactions that we just talked about. So first up is sodium sulfate. So I'll do that in the first test tube on the left. If I add some sodium sulfate to my unknown, we see that a precipitate does form. To the second sample, I'm going to add sodium iodide. And we see no precipitate form. Our third reaction is with silver nitrate. So if I add that to the third test tube, we see the precipitate forms. And then last but not least, we'll react with calcium nitrate. And no precipitate forms from that one. So now that we have our results, we can go through and see how those results match up with what we talked about before. We sort of predicted whether or not we would see a precipitate for each of our different options. So if we go through our 4 reactions, when we mixed our unknown stuff with sodium sulfate, we saw that a precipitate did form. So we know that it can't be potassium. A precipitate did form, so it has to be something that our cation, M, has to be something that is not soluble when it is paired with sulfate. So that narrows it down to either barium or lead. Our next reaction, when we mixed our unknown stuff with sodium iodide, we saw no precipitate form. So from the previous reaction, we had already ruled out potassium as an option, and now we didn't see a precipitate, so we know it can't be lead either. So based on this, we know that barium is our only option that is consistent with both of those results. So based on this, we know that our cation has to be barium. For our next 2 reactions, when we mixed our unknown substance with silver nitrate, we saw that a precipitate did form, which knocks out nitrate as an option. Nitrate is soluble with everything. So if we ever see a precipitate form from something, regardless of what the cation is paired with, the nitrate cannot be the anion. So that is narrowing it down to chloride or carbonate as our 2 possible choices. And then our last reaction, we saw no precipitate. We had already knocked out nitrate as an option previously, but now the absence of a precipitate when we reacted our unknown substance with calcium tells us that the only option remaining is that our anion is chloride. So we can kind of use process of elimination here to figure out, based on our experimental results, our cation was barium and our anion was chloride. So our unknown substance must have been barium chloride, which has a formula of BaCl2.